Welcome back to elementary statistics. In this video, we're going to be looking at organizing data. Once you have settled on your experiment, your observation, or whatever you are trying to analyze, you're going to acquire a hopefully significant amount of data and have to find some way to take it in, put it in somewhere that you can organize it, and then use that organization to make your conclusions. As we are collecting this data, we have to think a little bit about what kind of data we have first. So a little bit more vocabulary before we get into, well, I can't really call them computations, but more direct examples. First of all, if I can push the right button, there we go. First of all, the data you collect could be qualitative data or quantitative data. Right? Qualitative data means you're talking about descriptions of things. We're going to do an example in just a few minutes where we are looking at a bag of chocolate or candy-coated chocolate and analyzing what color each piece of candy in the bag is. Those colors are qualitative data. They describe it. They don't give you anything that you can do calculations on directly. Quantitative data is data that gives you a numerical measurement. Right. And this right away is something to pay attention to. We are not looking at, are we getting numbers out of this? Because you'll see that even in the qualitative data, we're going to find a way to get numbers to do some work on. We're asking here, when you are looking at the population or the sample that you are studying, is the thing you are studying qualitative or quantitative? Are you studying the color, the shape, the size? If you're collecting data on the size, are you just categorizing things as large, medium, and small? Or are you getting out a ruler or calipers or a mass balance and finding numerical values to describe that thing? Once you've collected the data, as you'll see in a couple of minutes, we're going to start looking at counting up how many times each option occurs. That's called the frequency. And the frequency is always numerical, but that doesn't mean the data isn't qualitative. If the measurement you are taking on each member of the population or the sample that you are studying is qualitative or quantitative, that's the thing we're analyzing here in the first step. Once you have that, we can continue onward. Qualitative data is kind of, that's the end. But when you have quantitative data, we can further classify that data as being either discrete or continuous. Discrete data uses counting numbers. For example, if you are rolling a six-sided die and recording the result of the die, the result could be a 1, a 2, a 3, a 4, a 5, or a 6, but nothing else. Because there are distinct differences, you're either here or you're there, you're nowhere in between. That's what we're talking about when we say discrete data. Continuous data is the opposite of that. Continuous data where you can fraction things down and look at a finer and finer scale. Sometimes you stop at some point. For example, if you're measuring people's heights, you might have a measuring tape that is marked to the nearest eighth of an inch. You can't get any more detailed than that, but still, you can get down a lot further, and there are quite a few different options. Um, so there can be a gray area in the middle, but when you're looking at counting numbers, when you're looking at here are the options and there's not really anything between, versus when you're looking at a large array of possibilities. Right. Talking about whole numbers and fractions and decimals is a generalization. There's more detail that I should get into than that, but it's a good starting point. With these ideas in mind, we're going to extend and have a slightly different classification. Um, Using those ideas of qualitative versus quantitative, discrete versus continuous, we can categorize our data as nominal, ordinal, interval, and ratio. And these are a little bit harder to understand. They're probably not vocabulary that you've used frequently. But this scale is the more important one because it's going to tell us what kinds of statistical tests we are able to do. There are some tests that are just not possible with some of these types of data. The way that I like to think about these, nominal measurements are categories without order. Ordinal measurements have an order, but the size of things can be arbitrary. Interval measurement is equally spaced order, and ratio measurement has the further caveat that zero is meaningful. Qualitative data can only fall into the nominal and ordinal categories, but quantitative data can fall into actually any of the four. The example that I've been giving of the colors of candy-coated chocolate is definitely nominal data. There is no order, right? Brown doesn't appear before red, brown doesn't appear after red. Whatever order makes the most sense to organize the data for yourself, but there's no natural ordering to those things. Compare that to, say, finishes. Excuse me. Compare that to, say, when you finish a race. First place, second place, third place, fourth place is a very definite order. It looks like numbers, but it doesn't really give you a sense of distance. The person who finished first place may have finished ahead of the person who finished second place by um, inches, photo finish. The person who finished in second place may have been fully a minute ahead of the person who finished in third place. So the distinction between first and second and the difference between second and third don't have to be related to each other at all. You can't do arithmetic on these things, right? First place plus second place is definitely not third place. So that's what I mean when I say ordered but arbitrary. Another place that ordered but arbitrary comes up is in opinion and satisfaction surveys. On a scale of 1 to 10, how much do you enjoy using this product? Well, sure, on a 10, you're going to like it more than if you liked it at a 9. But your idea of a 9 and my idea of a 9 might not quite line up with each other. Your idea of a 7 and my idea of a 7 might not quite line up with each other. It gives you a sense of order. Calling it a 10 out of 10 is better than calling it a 3 out of 10. But it doesn't give you a sense of scale to that. If this product is an 8 and that product is a 7, versus if this product is a 4 and that product is a 3, between those two pairs of products, how much better is one than the other? I don't know. I don't have that kind of information because of the way that that measurement took place. Interval starts to get to things that you can actually calculate. The difference between interval and ratio can be a little bit hazy at times. So I like to talk about them together. 0 is meaningful. If you are measuring heights, if you're measuring weights, if you're measuring times, 0 is almost certainly meaningful in those cases. You have ratio data. A very obvious place where 0 is not meaningful is in temperature scales. If it is 0 degrees, sure, that is a measurement, but it's not the baseline measurement. It can be -5 degrees out. So when negative values are useful, very often that turns into interval data. When 0 as a baseline, and you can't go lower than 0, that tends to be ratio data. That's a distinction that we're not going to worry about all that much in this course. But that idea, temperature scales, 0 is at an arbitrary point in the Fahrenheit or the Celsius scale. Compared to weights, there is no arbitrariness to 0. If something weighs 0 pounds, there's nothing there. Right. And so I hope just from that, you can start to see why these different levels of measurement become useful. When you have nominal data, there's not a lot you can do with it as far as trying to do calculations and work with the data. When you have ordinal data, you get a little bit more. When you have interval data, you get quite a bit more. And then ratio data gives you more information still that you can use, more ways you can do calculations on the data. Let's start with that idea of nominal data that I mentioned earlier. All right, get this slide out of the way. We are going to draw a candy-coated chocolate from a bag, and we are going to record its color. All right. You can, if you want to, pause the video and record all of these. I'll also have the text of this distribution listed in the description of the video. We've got a whole bunch of colors: brown, red, brown, brown, red, red, green, orange, brown, red. red, red, brown, orange, red, brown, green, yellow, red, 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 yellow, red, green, orange, etc., etc., etc. And we have done this in the most useless way possible to record all of this data. We've just listed out color by color as it came up. I hope that as an adult who has experienced the world, you wouldn't think of presenting data this way. And I wouldn't record data this way, but I have to talk about this because it is a reality of a test-taking environment. If I'm going to give you an exam and I want you to do an analysis on the data, I can't just hand you something and say, here, do the experiment. I have to package it in some way for the exam. And a list like this is what I'm probably going to end up giving you. What I want you to think about on this list is not just it's a wall of color, but one by one. I pulled a candy out of the bag. I looked at the candy. It was brown. I wrote that down. I pulled a candy out of the bag. It was red. I wrote that down. I put that candy aside, or maybe I ate it. I got a brown one, another brown one, a red one, and I just go through taking candies out of the bag one by one and writing down the color of each one in the order they appear. It's not a good way to do this, but it is a way to do this. And the advantage of this way of doing it is that if I give this to you, you can understand exactly what happened in the experiment, and you can go on to do the analysis as though you were doing the experiment, even though you don't have the bag of candy in front of you. Instead, probably what any sane person would do, looking at a set of data like this, would be to, let's scroll this a little bit, not too far, just a little bit, so I have a bit more room below. What any sane person would do is set up a table with colors and tallies. Let's see. We've got brown. That's the first one. We've got red. That's the second one. We've got brown again. We've got brown again. We've got red again. I'm not going to keep this up forever. There's a third red. Then we go to green and orange before going back to brown, red, and red. And that's how far I wanted to get on this. The idea of tally marks, you just put ticks down. Once you get to the fifth one, you put a line across so that when you go back, it's relatively easy to count. I'm not going to record going through the rest of this, but I am going to fill out the rest of this table. All right. And so this table with the tally marks greatly simplifies the wall of text that was the original bit of data. If I was doing this experiment and not relying on something that I had printed out to use on an exam, this is probably how I would collect the data in the first place. I would look at sample by sample, I would write down the color, and I would just start filling in the tally marks as I went. It's fairly straightforward. It's a fairly easy way of collecting the data, and it certainly works. Now that I have it, I'm actually going to simplify it even further because I can count out pretty quickly and figure out, oh, I've got 17 and 18 and 7 and 4 and 7 and 2. But why go through all that when I could just write it directly? And once I do that, I'm going to produce an object called a categorical frequency table. I've got my measurement, color in this case, and I'll list out my colors. brown, red, green, orange, yellow, and blue, and list out my frequency. We're going to very often in this course use the variable f to denote a frequency. And you can be pretty confident that whenever you see an f, it is supposed to be representing a frequency. Let's see, brown had a frequency of 17, red had a frequency of 18, 7, 4, 7, and 2. All right. So this is a categorical frequency table. This is the kind of thing that is our starting point for most of the statistics that we're going to be doing in this course. Sometimes instead of seeing it called a frequency table, you will see it called a frequency distribution. There is a specific difference between the meanings of those two terms. The frequency table is the thing that you write down on the paper. The frequency distribution is the bag of candies itself. For our purposes, it's not going to make that much of a difference, but there is that distinction, right? The frequency distribution is what the sample, the bag of candies, looks like. The frequency table is how you put that information onto a piece of paper. Oops, sorry about that. That's the button I wanted. Now that we have this frequency table set up, we can find our first statistic, our first measure, which describes the distribution, the sample of this one bag of candy. Specifically, we're going to look at the statistic called the size. What is the size of this frequency distribution? Well, the size of a distribution is denoted using a lowercase n, and it's calculated as sigma f. Depending on your mathematics background, you may or may not have seen this symbol sigma before. All right, this is a capital sigma. A lowercase sigma is also going to come up. Capital sigma kind of looks like a capital M turned on its side. And we read it as the sum of. So n is the sum of the f's. In this case, our f values are 17, 18, 7, 4, 7, and 2. If we add those things together, 17 plus 18 is 35, 35 plus 7 is 42, 46, 53, 55. So our size of this distribution is 55. Fairly straightforward statistic to calculate. Things have gotten a little bit crowded here, so I'm going to use the nicety of a digital touchscreen to copy that categorical frequency table onto a clean slide and extend it out. so that we can create one more category, which I'll call the percent frequency. To calculate these percent frequencies, I am going to need my calculator. And a percent frequency is just the percent of the distribution, which is that score. So for the first one, we'll take the frequency of brown, which is 17. We'll divide by the total size, which was 55. We'll type that in correctly. My calculator tells me it's 30.909. All right, you can multiply by 100 to convert from a decimal to percent. I'm going to go ahead and round things to the nearest whole percent. All right, that's a formula that should be fairly straightforward. Percent is F divided by N. Um, let's see, just continuing these calculations. For red, I get something in the ballpark of 33%. For green, I get something in the ballpark of 13%. Um, orange comes out at 7%. Yellow is also 13%. And blue is 4%. If you add these together, 31, 33, 13, 7, 13, and 4, in theory, you should end up at 100%. 100% of the distribution is in the distribution. In practice, it doesn't quite work out that way. For this particular table, it actually works out pretty terribly. I end up with 101%. But that's reasonable. I've rounded all of these things to the nearest whole percent. And if I round everything to the nearest whole percent, depending on what the numbers look like, I could end up with the total being anywhere from 96% to 104%. So 101 isn't all that bad by comparison. Let's move on and look at one more distribution of data. This time, I am looking at the record high temperature for each state given in degrees Fahrenheit. And I could record which state is which. I think if I remember correctly, these are given in alphabetical order by state, but that's not what I really care about. Once again, I'll have this data listed out. I don't know if it's still up to date. I don't have which temperature corresponds to which state. That's not really what's important. But if you want to copy it down, you can pause the video and do so. What I want to point out immediately on this distribution is that marking down with tallies isn't really going to save us. Sure, there's a couple of scores that get repeated. All right, 120 is relatively popular. It shows up, I know there was another place, there it is, 3 places. 114 shows up a couple of times. But for the most part, each score, each temperature is different. So trying to use a tally and set up a frequency table isn't quite going to help. And so for this problem, we're going to set up what's called a grouped frequency distribution. A grouped frequency distribution is going to cause us to lose information about the sample. It's going to force rounding error to occur. But the trade-off of that is that it's going to allow us to analyze the data very quickly and very readily. So there are pros and cons. Depending on what you are trying to do, they may or may not be valuable. When you want to make a grouped frequency distribution, the first thing you need to do is determine how many groups to use. Determining how many groups is actually generally not going to be your responsibility, at least for this course. But moving onward, if you're actually performing statistics somewhere, it might become something that is important. And so my rule of thumb is the square root rule. There are 50 data points in this distribution. And if I calculate the square root of 50, I get this terrible number that is really close to 7. That's my starting point. I'm going to think about this distribution and say, well, maybe 7 groups is going to be nice. Maybe I'll try 6, maybe I'll try 8. If I'm doing this using computer software, I'll go through and do several group frequency distributions quickly and look to see which one is actually producing that right balance between it's readable and we're losing too much information. So again, coming up with how many groups to use is more of an art than a science. And it's not something I'm going to specifically ask you to figure out in this course, but there's the reasoning that I tend to use when I need to do this. All right, so we're going to go with 7 groups in this particular case. I am then going to look through my distribution and figure out the maximum and the minimum values that appear in the table. See, the maximum value, I kind of just do this playing a hovering game. Hover over a score, wait until you find something even bigger than it, and if you never do, then that's the maximum. And it looks like that is, in fact, the maximum, 134. And then just the opposite for the minimum. Right? Hover over a score. If you find something smaller, then you jump to that. And we just keep looking at everything. I don't see anything that is lower than 100, so there's my minimum. And once I have the maximum and the minimum, I can calculate the range by subtracting these things. And I can take my range of 34, I can divide it by my 7 groups. And I can round. Now here's something that can be a little bit confusing. When you do this calculation, you always have to round up. In this particular case, that's kind of obvious. We want to round up anyway. 4.8 rounds up to 5. But in general, even if it came out to 4.123, we would want to round that up to 5. The reason for that is that if we round down, we're not going to have enough material to cover the entire range, and we're going to end up with more than 7 groups. If we round up, we're going to end up with some unused stuff. And we have to play a bit of a balancing game again to try to figure out whether we want the unused stuff to be at the beginning or at the end. But this particular distribution is chosen so very carefully that this works out perfectly for us, or almost perfectly for us. Our minimum is 100. And if we count 100, 101, 102, 103, and 104, the next group is going to start at 105. And we realize that we're just going to add 5 each time. 110, 115, 115, not 150, 120, 125, and 130. All right. So the last score in the last group, 135, well, oops, keep pushing the wrong button. The last score in the last group is 134. The next score would be 135. And again, very conveniently, this lined up perfectly. We got every single piece in this distribution with nothing left. That doesn't always work. In fact, that doesn't usually work. Sometimes you'll want to start lower than the minimum score, right? Instead of starting at 100, I might have started this at 99 or at 98. Instead of ending at 134, I might have ended at 135 or 136. As a general rule, if your first or your last group are not the same size as the rest of the groups, that's okay. But the one thing to pay attention to is the first and last group should be in equal size. Right? So if we had the last group ended up 134 to 138, well, that's a problem because almost that entire group is outside of our distribution. So we want to shift everything down so we get equal amounts outside at the top and at the bottom. All right, but we can go through, we can count up data point by data point. Our first entry was 112, which is somewhere between 110 and 114. Our second entry is 110, which is again somewhere between 110 and 114. 107, 116, 120, 100, 118, and so on. I'm not going to make you watch me do the entire tally. All right. But I do encourage you to do the tally on your own. Check my results, make sure you're getting the same thing that I am. And once we have that tally, we can use it to write out our frequencies. In this case, 2, 8, 18, 13, 7, 1, and 1 are the frequencies of the groups in this grouped frequency table. When it comes to a grouped frequency table, there's a couple of other pieces of vocabulary that are worth looking at. I've been calling these the groups. That's certainly a valid name. It's not the only name. Our textbook likes a different terminology, which is the classes. It means the same thing. You group the data into classes, which gives you some distinction between the action and the object instead of grouping things into groups where the action and the object have the same name, which can be a little bit confusing. Um, the other thing that I want to look at here is that this thing that I had originally called the groups, we're often going to call the class limits. Right? The limits aren't the only way we can talk about the class. Sometimes it's more useful to talk about the class boundaries. The class limits take values within the class. The class boundaries very specifically are looking for values outside of the class. The first class boundary is the hardest one to do, so I kind of leave that to the end. And instead, I look at the next bit. The first class ends at 104, the second class starts at 105. The boundary for the class is the point halfway between those. So in this case, it's 104.5. Then the upper boundary, again, this class ends at 109, this class begins at 110. Halfway between those is 109.5. One of the advantages of thinking about classes in terms of boundaries is that the upper limit or the upper boundary of one class is exactly equal to the lower boundary of the next class. The other nice thing about class boundaries is that the class boundaries are never directly data values in the distribution. They are always between data values. And so you never have to worry about remembering, am I counting this one as part of that, or is that part of the lower one? It saves you from that headache. So we can fill out the rest of those without too much thought. The first and the last class boundary are a little bit more complicated. They are a matter of pattern recognition. In this case, I notice that the lower boundary is 0.5 smaller than the lower limit. So I just take 100 minus 0.5 and I get 99.5. All of my upper boundaries are 0.5 higher than the upper limit. So I just take my last upper limit, add 0.5 and get 134.5. All right, going from class limits to class boundaries, for the ones in the middle, you just take the average, you look for the pattern, and you use that to figure out what is happening. All right, my next column in this grouped frequency table is going to be labeled as X sub M. I'll get to what X sub M means in just a moment, but before I scroll off the screen, I want to make sure that my last column of frequency gets copied over correctly. Now that I have that, let's think about this X sub M column. All right, X sub M is called the midpoint of the class, or the class midpoint. And you can calculate the class midpoint by averaging the class boundaries. So for the first one, we want something halfway between 99.5 and 104.5. So take those, add them together, divide by 2. And in this particular case, we get 102. take 104.5 plus 109.5 and divide by 2, and we get 107. Then just continue doing that calculation for each of these data points, for each of these classes. And we get those midpoints filled in. The purpose of a grouped frequency distribution is specifically to get these midpoints. The midpoints are our rounding goal. If you go back and look at what we've done, what we've actually done is found these midpoints and decided that these midpoints are going to represent all of the data in the distribution. And we take each data value and we round to whichever of these is nearest. And then we create a frequency distribution on that. Saying that that's what we're doing is kind of convoluted and complicated. And that's why we talk about it in terms of the class limits or the class boundaries and creating the tally marks from there to find our distribution. But when it comes to using a frequency distribution, this is generally how we're going to approach it. We have our class limits, we have our class boundaries. We use those to figure out the midpoint. And then we take our midpoint and we use those midpoints as representative of each class. And we treat this as though those were the only data values in the distribution. Again, doing this caused us to lose information. Our statistical distribution is less precise now than it would have been originally. The trade-off for that is that we now have a frequency distribution and we can do work on a frequency distribution relatively easily. All right, I don't have anything for discussion on this one. We'll come back to the idea of frequency distributions in the next video. In the following video, we'll talk more about grouped frequency distributions specifically, and we'll have more to talk about on each of them at that point. So without any further ado, I'll wrap up here. Thank you as always for joining me. I'll see you in the next video.